All right, let's dive in. Today we're cracking open the cosmic rulebook, the one that governs pretty much everything, Einstein's theory of relativity. And trust me, it turns out the universe has some very surprising rules. If you take away just one single thing from our chat today, let it be this phrase right here. It depends on who's looking. This simple little idea, it's the key that unlocks everything we're about to cover. Time, space, gravity, none of it is set in stone. It's all, well, relative. So what's actually in this rulebook? Don't worry, we're not going to get bogged down in a bunch of crazy equations. The best way to think about relativity is as the set of principles for how the universe behaves at its most extreme. When things are going incredibly fast or are just unimaginably massive. In our regular, everyday lives, the normal rules we're used to still pretty much apply. So Einstein didn't just drop one bombshell theory on us, he actually split it into two main parts. You can think of them as two different chapters in that rulebook. One chapter is all about what happens at extreme speeds, and the other one is about extreme gravity. And here they are, the two big players. On one side, you've got special relativity. This is the one that totally rewrote our understanding of speed and time. Then, on the other side, we have general relativity, which just completely revolutionized our whole concept of gravity and this thing called space-time. Let's tackle them one by one, shall we? So, first up, special relativity. And maybe its most mind-bending consequence is this. Time itself isn't constant. Nope. The rate at which your clock ticks literally depends on how fast you're moving. Wild, right? Now, to get your head around how time can change, you first have to understand the one thing in the entire universe that doesn't, and that's the speed of light. Think of it as the ultimate cosmic speed limit. It's the fixed, unchanging benchmark that everything else gets measured against. No exceptions, period. Okay, so what happens when you start getting close to this universal speed limit? Well, the universe has to make a choice. To protect its absolute speed limit, it starts to get a little weird with something else we all thought was constant, time. For you, the person traveling that fast, time literally begins to slow down. This classic thought experiment shows you exactly how it works. Okay, picture this. You hop on a spaceship and take off from Earth, zipping along at close to the speed of light. To you, on the ship, 1 year goes by. It feels totally normal. But when you get back home, you find that 10 years have passed for everyone else on Earth. Your time moved slower compared to theirs. This crazy effect is called time dilation. Whew, okay, so that's speed. But what about the other side of that cosmic coin? Gravity. With general relativity, Einstein didn't just tweak the old ideas about gravity. He basically ripped up the old rulebook and started from scratch with an idea that was way more elegant and a whole lot stranger. Before Einstein, we were all taught that gravity was this kind of invisible force, like a rope pulling things toward each other. But Einstein's revolutionary idea was, get this, there's no pull at all. Gravity is just what we feel when we're moving through a universe whose very shape has been bent and curved by mass. And to understand that, we need this key concept, space-time. See, Einstein realized that space and time aren't two separate things. They're actually woven together into a single four-dimensional fabric. It's the stage where the entire universe plays out. You can't mess with one without affecting the other. The trampoline analogy is honestly the perfect way to picture this. So imagine space-time is a big, stretched-out trampoline. Now, if you put a heavy bowling ball, let's say that's the sun, in the middle, what happens? It creates a deep curve, right? A big warp in the fabric. Now, if you roll a little marble, that's the Earth, nearby, it's not being pulled by the bowling ball, it's just following the curve that the ball made. That path, that's what we experience as gravity. I know, this all sounds incredibly cosmic and far out, doesn't it? Warped time, bent space. But what if I told you that you actually rely on these bizarre rules every single day, using a device that is probably in your pocket right this second? And that's a totally fair question. If reality is this flexible, why does everything feel so normal, so solid and predictable? Why don't we see clocks ticking at different speeds or feel the ground curving underneath our feet? Well, the answer is actually pretty simple. The effects are 100% real, but on our human scale, they are just incredibly tiny.
We move way too slowly to notice any real time slowing down, and the Earth, while it feels massive to us, just isn't heavy enough to create a warp in spacetime that our senses can pick up on. But our senses aren't the only way we measure the world. We've built these incredibly precise instruments that can detect these effects. And one of them is so common that if it failed, it would cause absolute chaos worldwide. That's right, your GPS. Without Einstein's theories of relativity, the global positioning system would be so wildly inaccurate it would be completely useless. In just a single day, the little dot on your map would drift by more than 10 kilometers. That's about 7 miles. And here's why. It's because GPS satellites get hit by both parts of relativity. Because they're moving so fast, their internal clocks actually tick a tiny bit slower. That's special relativity at work. But at the same time, because they're farther away from Earth's gravity, their clocks also tick a tiny bit faster. That's general relativity. Your phone has to constantly use Einstein's math to correct for both of these effects, just to tell you where to turn next. So let's do a super quick recap with this little cheat sheet. We've got space-time, that unified fabric of reality. We've got time dilation, the idea that moving faster makes time go slower for you. We have gravity, which isn't a pull, it's just the curve in that fabric. And of course, E equals mc squared. That famous equation, it's a key piece of special relativity, showing that energy and mass are just two different forms of the same thing. It's the idea that literally unlocked the atomic age. And that really brings us to our final thought. Einstein showed us that the fundamental stage of our universe, space-time itself, isn't rigid and fixed. It's alive. It's dynamic and flexible. It can be warped, stretched, and changed. And that leaves us with this incredible question. If the very fabric of reality can bend, what other rules are we just waiting to discover?